Hey, welcome back. In this video, we're going to continue to discuss matching, but we're going to focus on matchings in bipartite graphs. We're going to see some algorithms, and we're also going to prove another theorem. So just to quickly review the relevant definitions, we have a matching in a graph G, and that's just a set of edges with no common vertices. We also have maximal matchings. These are matchings that are not subsets of any other matchings in the graph. And we also have maximum matchings. And a maximum matching in a graph is a matching of maximum size in that graph. An example that we saw in the last video was this graph P4. I'm going to draw two copies of it. I'm going to circle the edges in this matching. So on the left, the P4 on the left, there's a maximum matching. And the P4 on the right, here is a maximal matching. So that matching on the right, we can't add any more edges to it because all the other edges have vertices in common with that edge. Another example we saw, a non-path. This one we saw in class. That one's maximal, but not maximum. For a maximum one, we could take these two, for example. So we can get two edges in a maximum one for that graph, the K4 minus an edge. So in the video today, we're going to focus on bipartite graphs. And in particular, we're going to focus on trying to find maximal matchings in bipartite graphs. So one application of matchings in bipartite graphs specifically is this application when you have a bunch of courses and a bunch of rooms, like at a high school or a college, for example. And we assume there are S courses and T rooms. And we're also assuming that all of these courses meet during the same time period. So like back in high school, if you had like 7 or 8 time periods, we're talking about just the courses for one of those time periods, like the period 4 courses. So we know that in high school and in college, there's courses that can only use some of the rooms. So for example, you might want to have the course close to the teacher or professor, like if they have some kind of mobility issue. Also, some rooms have more seating capacity than others. So if it's going to be a course with a lot of students, you want a lot of chairs in the room. Also, some lab courses, you might want to have some equipment like a Bunsen burner or something. So that could also be a constraint on the rooms. So assume that for each course, we know the list of possible rooms for that course in advance. So we can construct a graph, a bipartite graph specifically. We'll call the parts L and R for left and right. And the L part is going to have a vertex for each course. So if we name our courses course 1, course 2, all the way up to course S, because there's S total courses, then we'll let the vertex UI represent the course I. And on the right side of our bipartite graph, we will have T vertices for each of the T rooms. And if we call the rooms room 1, room 2, up to room T, the vertex VJ will represent the room J. And how do these vertices represent the courses in the rooms? More specifically, we put an edge in our graph UI VJ if the course I can meet in the room J. And if we want to schedule as many courses as possible during this time period, then we can find a maximum matching in this graph. So before we focus on the bipartite graphs, we're first going to discuss how we would find a maximum matching in any graph. And then we will focus specifically on the bipartite graph once we have an outline of a solution for any graph. So we proved a really useful result in last week's video. And this result, it's called, some people call it a lemma, people call it a theorem. It's called Burge's lemma/theorem. And in order to state it, we need to recall a term that we defined last week. So we defined this term augmenting path. And it's an augmenting path for a specific matching. We'll call it M. And that's a path that starts and ends with vertices that are not in any edge in M. And it alternates between edges not in M and in M. So for example, if we had this path right here, and we say that this vertex right here is not in M, so we call such a vertex free, as we defined in last week's video. Same with this one on the end, that one's also free, it's not in M. And the edges on this path that are in M are this edge and this edge. So that would be an augmenting path for M. Another augmenting path for M is just a single edge that is not an M, and both these two vertices are free. So these are two examples of augmenting paths. And the P4 we saw earlier, that one, if we had the edge from the matching in the middle, that would be an augmenting path for the matching if both this and this were free for M. So one thing to notice here, which we observed in last week's video, is that the number of edges on these paths, the augmenting paths, it's always going to be odd because it has to alternate between edges being not in M and being in M, and it has to start and finish with edges that are not in M. So there have to be an odd number of edges. And what we proved in the last video, this really useful result that's going to give us an algorithm for finding maximum matchings. We proved that a matching M is maximum if and only if there's no augmenting path for M. And we can use this result to give us an algorithm for finding a maximum matching in any graph. And we're first going to write the algorithm and not describe how we're going to do one of the components of the algorithm. And then on the next slide, we'll discuss how we do that component for bipartite graphs. So here's how our algorithm is going to start. We're going to start just with an empty matching, so no edges in the matching. And then we're going to try to find an augmenting path for this matching. If the matching has an augmenting path, in other words, by Burge's lemma, if it has an augmenting path, that's true if and only if the matching is not maximum. So in that case, we replace the matching M with M minus P union P minus M. So this is the symmetric difference of the sets M and P. And when we take that symmetric difference, we can see that the size of the new matching it's going to have a size that's one higher than the size of M. And why is that? So we can look at an augmenting path. For example, let's say we have some matching up here in some graph. Here's our matching. So M has this edge, it has this edge, and it has those two as well on the augmenting path. So when we replace M with M minus P union P minus M, we still have all of the edges outside the augmenting path. So we still get these. And then on the augmenting path, we're switching out the edges in M on the augmenting path for the edges not in M. And as we just noted before, there's an odd number of edges. And we start with edges not in M, and we finish with edges not in M on the augmenting path. So there's going to be one more edge not in M than there is in M on the augmenting path. So we're going to be taking these edges, and we're going to end up with exactly one more edge in the new matching than we did in the old matching. And that's because we replaced some number J of edges on this augmenting path, replaced J edges with J plus 1 edges on that augmenting path. And in our picture here, J was 2, and we replaced it with 3 edges. The picture here, J was 1, we replaced it with 2 edges. And then this one right here, that was just J equals 0, and we replaced it with 1 edge. So the size of the new matching was 1 more than the size of the old matching. And we go back to step 2 with that new matching as our new M, and we try to find an augmenting path for that new matching. And if the new matching is maximum, we won't be able to find any augmenting path. If it's not maximum, we will be able to find an augmenting path. And we'll just do the same step again, step 3. We'll replace the matching with the symmetric difference of the matching and the augmenting path. And if the matching is eventually maximum, then we will hit step 4. And if we hit step 4, that means we found a maximum matching. So we don't go back to any step. Our algorithm is done at that point. And so this gives us an algorithm for finding a maximum matching in the graph, but there's part of it that we haven't really described. And how are we going to do this part? How are we going to find that augmenting path for the matching M? And if we have a way to find the augmenting path, the rest of the algorithm, we have described exactly what we're going to do with that augmenting path. It's just this part right here, we were very vague. We didn't say how we're going to find that path. So now we need to talk about how can we find that path? And we're going to focus on how to find that path in a bipartite graph. But before we do that, I just want to mention everything on this slide applies to any graph. So we didn't make any assumption about the graph being bipartite on this slide. So the only time that we're going to assume that the graph is bipartite for this algorithm is on the next slide when we show how to find an augmenting path easily for bipartite graphs. So that's going to be the next slide. We will focus on bipartite graphs. And this slide that we just did is fully general for any graphs. So when our graph is bipartite, let's look at how we can find an augmenting path. And the way we're going to do this, it's interesting. We're going to start with this undirected graph, G, and some matching in G, which we call M typically. And we're going to turn G using the matching into a directed graph. So we're going to get a new directed graph using both G and this matching M on G. So there's our bipartite graph G. We'll say that it has parts L and R. And maybe I'll draw a picture. So here's L, here's R, and we'll have some edges in this graph. So the edges that I'm circling here will be the edges currently in M. So there's a picture of G. So G is pretty small here. And we're going to construct a directed graph from G and M. So our M, we've circled the edges in M. And this directed graph is going to use M to determine the direction of the edges in G. So we will direct edges from the left side to the right side if they are not in our matching. So this edge, not in the matching, it gets directed that way. Same with this edge, and same with this edge. And now we also have to direct the edges that are in M. So the edges that are in M go from R to L. So this one gets an arrow here, and this one gets an arrow here. Now we add some new vertices. So here we'll have a vertex X, and over here we'll have a vertex Y. Now we're going to put a directed edge from X to any vertex that is not in any edge in the matching. That is an L. So we're only going to have edges from X to vertices of L. And we can look at this first vertex of L up here. That one is in an edge in the matching. So we put there's no edge from X to that. Same with this one. That one's also in an edge in the matching. So no edge from X to that. We do put an edge from X to this one. This one's not in any edge in the matching. And same with this one down here. That's not in any edge in the matching. So we put an edge from X to that. Now, Y over here, we have directed edges to Y from all vertices in R that are not in any of the edges in the matching. So this one at the bottom, not in any edge in the matching. This one right here, also not in any edge in the matching. The next one up, that is in an edge in the matching, this edge right here. This one right here, that one is not in any edge in the matching. The one at the top is clearly in an edge in the matching, this edge right here. So those are all our edges to Y. So we have 2 edges from X to L and 3 edges from R to Y. And now what we need to do is just find a shortest path from X to Y in this directed graph that we constructed. The directed graph, we call it D for directed graph. we want to find the shortest path from x to y. Any path from x to y would be fine, but we'll just find the shortest one. And the reason for that is because we can see that any path from x to y, well, the path, it's going to start at x, it's going to go to a free vertex, some vertex that's not in the matching. Then if it goes all the way to y, it means that it has to go through some edge that's not in the matching, and then it either goes straight to y or it goes through an edge in the matching, then another edge not in the matching, and then to y. Or it could go through another edge in the matching, then another edge not in the matching. And it can just alternate. So if we do have a path from x to y, it has to go to a free vertex. It has to alternate edges being not in M and being in M. And then the last edge in the alternation has to not be in M. It has to finish on this right side. So it has to be not in M because there's no edges in M that finish on the right side. And then it has to go to Y. So this is any shortest path from X to Y, and more generally, any path from X to Y in this directed graph. So if we can just find a path from X to Y, and then we take the X and the Y off, and the edge adjacent to X and the edge adjacent to Y, that gives us a shortest path. So that gives us the what we want here, the augmenting path. So that shortest path, we turn it into an augmenting path and for our matching it. So if we can find the shortest path from X to Y, if we strip off X and Y and the edges adjacent to them, that gives us an augmenting path for the matching it. Because the edge after the edge that's adjacent to X is an edge not in M. So wherever X goes, so we can look here in this example we have up here. So in our graph D, our directed graph D, we want to find the shortest path from X to Y. So we start at X here. We only have two choices from X. We can either go here, and if we go there, we get stuck. If we go here, then we can continue from there. There's only one choice. Then we get over here. So this is our shortest path. So this one that I'm circling here, and then I'll uncircle it in a second. But that's the shortest path from X to Y there. And we can see that if we strip off the X and Y and the edges adjacent to them, we're left only with this right here. And that's an augmenting path for M because we have two free, so that's a free vertex, and so is that. And the edge between them is not an M. So that's an augmenting path for M in that example we saw up there. But the way that we found that augmenting path, we only used our eyes. So if we had a much more complicated graph, we couldn't really find the augmenting path that way. So we need a more systematic way to find this shortest path, which gives us the augmenting path. So we found the shortest path from X to Y, this path that goes from here to here. We cut off the X and the Y and the edges adjacent to them, and we were left with this augmenting path in the middle. This one was a real small augmenting path for M. It only had a single edge, and the two vertices in that edge had to be free. Now we're going to look at, given any bipartite graph, how can we find this shortest path in general? And we're going to do that actually not just for any bipartite graph that we're turning into a directed graph. We'll just do that for any directed graph. We'll talk about how to do that. So how we're going to do that, we're going to use a breadth first search. And so we can look at an example of this. So I'll draw a graph up here, and then we'll run through the example together. And we'll say, here's our vertex X, here's our vertex Y. We're trying to find a shortest path from X to Y in this graph. This, we'll assume it's a directed graph here. Okay, so we'll initially label every vertex as unvisited. So I will label it U for unvisited. Each of them gets a U. We will initially label X with the distance label 0. So it gets a 0 here. And all the others will get distance label infinity. We'll set the current vertex as X. So the current vertex, I will put a box around it so it's distinguished. And then for all the unvisited vertices to which the current vertex has an edge, we will change their labels if the distance label of the current vertex plus 1 is less than their current label. So the distance label of the current vertex right here is 0. So 0 plus 1, we can look at both of the neighbors of our current vertex. So neighbor right here, it has current distance label infinity, which is larger than 0 plus 1. So we'll replace that with 0 plus 1, which is 1. Same with this one right here, this neighbor of X. And we're only considering neighbors that we can get to from X. So the edge has to go in the correct direction. So we're only able to get there from X because the edge is going from X to these vertices. So we replace both of these with 1. Now we mark the current vertex as visited. So this U becomes a V. And if we marked Y visited, we didn't, but if we did, that would be the end of it. Since we didn't do it, we keep on going. And if we did not mark Y visited yet, then we'll select an unvisited vertex with the minimum distance label. So it's possible there's multiple with the minimum distance label. We'll just pick one of them. We'll pick this one. So that's our new, this one right here. So I'll call this U right here. So that will be our new current vertex. This will be a V. And that's our current vertex. We go back to step 4. And step 4, for all the unvisited vertices to which this current vertex has an edge, set the distance label to be the minimum of their current label, or 1 plus the label of the current vertex. So the only unvisited vertex to which this one has an edge is this one over here. And maybe U is a bad name for this one. Maybe I will call it W, because we have these U's for unvisited. So that'll be W, that'll be fine. So W only has a single unvisited vertex, this Y over here. And we're going to change the infinity, which is larger than the distance label of W plus 1. We're changing it to the distance label of W plus 1, which is 1 plus 1, which is 2. And that's the only one we changed. And then we're going to mark this current one, this current W, we're going to mark it as visited. And once it's visited, we will switch the current vertex to an unvisited node with the minimum distance label, because we have not yet marked Y as visited. So this has not happened yet. So now our current vertex becomes the vertex V down here. And we can look at V and see, does V have any unvisited neighbors to which it has an edge? So is there any vertex that's unvisited to which this current vertex V has an edge? We can see V doesn't have edges to any vertex. So we're not going to change any distance labels with that V. And we're just going to cross out the U and make that into a V. I guess I shouldn't have called it a V right here. Maybe I'll call it like an upside down triangle. That should be fine. Then we have V for visited, U for unvisited, and our vertices will be named So our vertices up there, I guess they end up with some strange names. We got X, Y, W, and an upside down triangle. So we're almost done here. So our current vertex right there had no unvisited neighbors. So we turned it into visited. And then we only have one unvisited vertex left. And that is Y up here. So that becomes our current vertex. And we can look at all the unvisited vertices to which Y has an edge. So we go back to step 4. So for all unvisited vertices to which our current vertex has an edge, our current vertex being Y, and Y doesn't have an edge to any unvisited vertices. It does have an edge to this visited vertex, but that vertex already visited. It has a V on it. So we don't make any more label changes using this Y as our current one. And then we mark Y as visited because Y is our current C. So Y becomes visited. And if Y is marked visited, then we found the path, so we halt. So how do we find the path? Because it looks like we just found a few numbers here. So what we can do is we take Y and we see that the distance from X to Y that we found is 2. Then we can just backtrack and we can look at the neighbors of Y, which of them ended up labeled with a 1. And when I say neighbors, so we backtrack from Y. So if Y labeled with D, which V with edge to Y labeled with D minus 1. So if Y is labeled with D, that means that Y has distance D to X. And that means that there must be some vertex. I said that a little wrong. So we're talking about directed graph. If Y is labeled with D, that means that X has distance D to Y. So there's some forward directed path from X to Y with D edges on it. And that's the minimum possible number of edges that we can have on a path going forward from X to Y. So if Y is labeled with D, that means that there has to be some vertex with an edge to Y in our directed graph that's labeled with D minus 1. And that means there's some vertex with an edge to that vertex that's labeled with D minus 2, and so on. So we can just start at Y and backtrack to a vertex that has a label 1 less, and then a vertex that has an edge to that one with a label that's 1 less, and we just continue like this. So in this example here, our Y was labeled with 2. So our path has the Y on it. And then we look at the vertices with edges to Y, which of them is labeled with 1? Well, this one right here, there it is. So we include that vertex. And then we can look at the vertices with edges to this one right here. Which ones are labeled with 0? And that's the only one right there, it's X. X is the only one labeled with 0. So that would give us a shortest path from X to Y in this small graph that I drew. And if we had a greater distance label on Y, then we would have to backtrack a little more. So for example, if we consider an example here where we have X and Y, and then we take this directed graph. So this one, we can start with X is 0, all the others infinity. And then replace this infinity with a 1. Replace this infinity with a 1 plus 1 to 2. So we're just running through the algorithm doing this. And each time the current vertex, so current, it starts here, and then it goes here, and then it goes here. and we just cross that one out. So now the current one is here. There's our current one. And the distance label for the current one's 3 right there. So this one gets replaced with 3 plus 1, which is 4. And then this becomes our current one. And then this gets replaced with 4 plus 1, which is 5. And then that becomes our current one. And that one has no unvisited neighbors. So as the current one moves from left to right, all the ones to the left of it become visited. And this one at the end has no unvisited neighbors. So it doesn't make any changes to the distance labels. It becomes visited, and that's our distance from x to y. And in this case, we can see the backtracking. We start with this vertex y. We look for a vertex with an edge to y that has distance label 1 less. And that is this one right here. So we have y, and we have that one. And then we backtrack from that one. We look for a vertex with an edge to that with a distance label 1 less. There's that right there. And then we look for a vertex with an edge to that one with a distance label that's 1 less than 3. So distance label 2 right here. And then we just continue our backtracking. And that gives us our path from x to y. And this gives us the shortest path. I just want to emphasize again, it wasn't even important for it to be a shortest path. It could be a path of any length for our purposes of finding an augmenting path for a non-maximum matching. But this algorithm that we just discussed, this works even if we want to apply to other situations, like any directed graph, not just a directed graph created from a bipartite undirected graph. Also, this algorithm we discussed, you can easily write this algorithm for undirected graphs. So you can actually just take this algorithm, and if you have some undirected graph, you can turn it into the directed graph with, for each edge in your undirected graph. So for example, let's consider this graph right here. This example will make it pretty clear. So if we have this graph right here, we can run the algorithm at the top on the directed graph, this one right here. So we take our undirected graph, but replace each of the edges with a bidirectional edge in the directed graph. And if that's our x and that's our y, so we can find a shortest path from x to y in the undirected graph by finding a shortest path from x to y in this directed graph. So you could apply the exact same algorithm just to that directed graph, or you could slightly rewrite the algorithm. So instead of saying unvisited vertices to which C has an edge, you can just look at unvisited vertices for which there's an edge that includes that vertex and C. That's what you'd say for an undirected graph. So we no longer have from and to in an undirected graph. And that's the only difference. I'll also mention, so this algorithm, I said before I put it up here that it's a breadth first search. So if we looked at a more general situation where we consider a weighted graph, like for example, we might want a weighted graph if our edges represented streets or trails between different locations, and the weights maybe are like the length of the trail. So if we used a weighted graph, we can modify this algorithm a little bit. We can replace this +1 with the weight of the edge between C and B, the current vertex, and the unvisited vertex that we are relabeling. And just by changing that +1 to plus the weight, we can get an algorithm which finds a shortest path even when the edges have weights. So this algorithm that I put up here is just a special case of a more general algorithm that works for weighted graphs. And we would just replace that +1 with the weight. And that more general algorithm is known as Dijkstra's algorithm. And the one we described here, this is just a breadth first search. So this is the unweighted version. And this is all we needed. So we were trying to find a maximum matching in a bipartite graph. So we started with the empty matching, and then we kept on finding augmenting paths for our matching. and then taking the symmetric difference with the augmenting path, replacing the matching with the symmetric difference until we obtain a maximum matching. In other words, until we couldn't find any augmenting paths. So we needed to find some way to get augmenting paths. So our way of finding augmenting paths, we turned our bipartite graph into a directed graph. And we find a shortest path in the directed graph that we construct. So we just finished up our discussion of the algorithm because we talked about how we can find that shortest path in the directed graph. And now that we know how to do that, we have all the pieces that we need of the algorithm. And there's one question left that I want to ask you about, though. So from this algorithm, hopefully it's pretty clear that this algorithm runs in polynomial time in the size of the graph. And I say size of the graph because this algorithm we discussed, it can be slightly modified with the wording to work for an undirected graph. And when I say size of the graph, for the directed graph version, I mean size of the digraph. So when we say size, we just mean order, number of vertices. So in polynomial time, in the order of the graph or digraph. And the problem for you to think about is, why does this algorithm that we just discussed run in polynomial time and the size of the given digraph or graph? So in the order. So we talked about this application earlier, this application for bipartite matching, where we represent classes as one side of a bipartite graph, and we represent rooms as the other side. And then we find some way to schedule the classes in rooms that work for those classes. And this is a typical problem for maximum matching in a bipartite graph. But a natural question that we might want to ask is it possible to schedule all of the courses? And we might want to have some kind of criterion to determine, given these courses, given these rooms, given the subsets of rooms that each course can be placed in, can we say if it's possible to schedule all the courses during this time period? And one way we could answer that, we could take the graph that we construct. So this graph G. So G has L, R. These are the courses. These are the rooms. And we could just do what we discussed on the preceding slides, but do that on G. So we can just find a maximum matching in G. And we could use the method we discussed. So we could start out with an empty matching and then find augmenting path P, and then replace the matching with the symmetric difference of itself with the path. And then we repeat until we cannot find any more augmenting paths. So we use that algorithm, and in order to find the augmenting paths, we turn our G into the directed graph. So remember, we introduced these vertices X and Y. We put edges to the vertices in L from X that are not in the matching. So we have some edges in our matching. Then we have these edges there. And then we have these three edges over here. So edges from R to Y for vertices that are not in any edge in the matching that are in R. So we turn G into this directed graph, D. And then we find a shortest path in that directed graph. And this directed graph So there are a few things I didn't draw there. So the directions of the edges in the matching go from R to L. And if we have any edge, so the one I drew doesn't have any edges outside the matching in the middle. So it actually is a maximum matching, the one I drew there. And we can see that in this graph that I drew, this G graph, where that G graph, the one we started with, it only had 2 edges. We can see that if that represented our classes in the rooms, it would not be possible to schedule all the classes for that graph. And our algorithm would tell us that because we would look for a shortest path from X to Y in this graph. And we wouldn't be able to find any because the only edges from X go to this vertex and this vertex. And there's no edges out of those 2 vertices. So we would get stuck at either of those vertices. So there would be no shortest path from X to Y there. And that would tell us then that we wouldn't be able to find an augmenting path for the given matching. And so we would be halted at this matching right here. So the fact that this matching doesn't have all the vertices on the left side and some edge, that would mean that we cannot schedule all the courses during this time. So we could just use the algorithm that we discussed to answer the question. So we can use the algorithm to find the maximum matching in the graph that we construct, this bipartite graph G. And based on this, we can say, no, for this example, for this specific example, we cannot schedule all the courses if that graph that we drew, so these are both the same graph. This is a little cleaner version of it because it's before we turned it into the directed graph. So we can say that if that's our graph representing which courses can be in which rooms, then definitely we cannot schedule all the courses at the same time. And it's not even the problem. So this graph, the problem with this graph is not even scheduling courses at the same time. It's that these 2 courses down here can't even be scheduled at all with a set of rooms. We didn't put any edges from these 2 vertices to the rooms on the right side. So that's the issue here. But the answer is still no. We cannot put these courses in these rooms. Now, that example, it was pretty easy to see that one. If we had any arbitrary bipartite graph, we could still apply the same algorithm we discussed. We find its maximum matching. If its maximum matching has all the courses as vertices and edges in the matching, then we're able to schedule all the courses. And if the maximum matching is missing some course, so if there's some course, some vertex on the left side that's not in any edge in the maximum matching that we find, then it means that it's not possible to schedule all the courses. Because if it was possible to schedule all the courses, then it would be possible to find a matching that's larger than that maximum matching. So this algorithm for finding a maximum matching does tell us if it's possible to schedule all the courses, or in other words, if it's possible to find some matching that includes all the vertices on the left side in the edges. Now we're going to find a faster way to be able to tell if a bipartite graph has a matching in which the left side, all the vertices on the left are in some edges in the matching. So we're going to find a pretty simple criterion. So we won't need to run this algorithm to answer the question. We'll just be able to check this criterion. And it's called Hall's criterion. And proving that this criterion actually tells us whether or not the bipartite graph has a matching in which all the vertices on the left are in edges in the matching. So the fact that the criterion works, we're going to prove that. And the proof of that is known as Hall's marriage theorem. So this is the question that we're answering. Can all the courses be scheduled? Like all the courses in this specific time period? And so the name of the theorem that we're going to prove to answer this question is Hall's marriage theorem. And in order to state the theorem, I want to introduce some terminology. So if we have some bipartite graph, say we have some graph G, bipartite, and it has parts L and R. And let's say we have, put 4 over here, and then we'll have a bunch over here. And I'm going to draw my matching now. This is just a matching. So we call a matching on a graph, bipartite graph G with parts L and R. We call the matching L perfect if every vertex in L is in some edge of the matching. So this one's L perfect because we see every vertex in L is in some edge of that matching. It's not R perfect, but it is L perfect. And we could also consider another example. This one is not L perfect. Why is it not L perfect? It's because of this one right here. That's the problem. That one is not in any edge in the matching. And as usual, I'm drawing my matching M just by circling the vertices, circling the edges in the matching. And I should have actually drawn the edges there. So there, I'll put them in there now. Okay. I might put some extra edges in there too that are not in the matching. Okay. So we have a non-L perfect matching up there. And we have an L perfect on the right. And we're also going to use this notation, n sub g of x. And that's going to be the set of all vertices in G that are adjacent to some vertex in X. So I want to illustrate this notation. I think it would be good to look at some examples just to make sure that one's clear. So let's consider this cycle right here. So I think that's a C9. And we can take X. So for the cycle, we shouldn't do a C9. This is not bipartite, right? It's an odd cycle. Wouldn't want an odd cycle. So let's make it slightly smaller. Let's make it a C8. There we go. Okay. So we can take our L set to be 1, 3, 5, 7. And we can take the R set to be 2, 4, 6, 8. And we'll take a subset of L. We'll say let X equal 1, 3, for example. Then in this case, for this graph that we just drew, if this is our G, so n sub G of X let's look up at that definition. It's a set of all vertices in G that are adjacent to some vertex in X. So 1 is a vertex in X, and so is 3. So 2 is adjacent to both of them. 8 is adjacent to 1, and 4 is adjacent to 3. And none of the other vertices are adjacent to either of them. So this is going to be the set 2, 4, and 8. So that's the set n sub g of x for that example. We can consider one other example. So P11 right here. And we'll have L. So this will start at 1, it'll go to 11. So L will be the set 1, 3, 5, 7, 9, and 11. And R will be the set 2, 4, 6, 8, 10. And we could take, let's say, the set X equals 3 and 9. So 3 and 9, in this case, are ng of x. Let's put that a little lower. The ng of x. So this is g over here. Ng of x would equal 2, 4. Those are the neighbors of 3, the only neighbors of 3. And 8, 10, the only neighbors of 9. So those are two examples of ng of x, this notation. And we have two examples of an L perfect and a non-L perfect at the top. So here's the claim of Hall's marriage theorem. The claim is that the graph G, and this, just to emphasize, this is a bipartite graph. So bipartite graph G. So this whole slide, we're assuming it's bipartite all the way from that second bullet. So G has an L perfect matching if and only if the cardinality of x is less than or equal to the cardinality of n sub g of x for every subset x of L. So our G right here, G has L and R, and X is just some subset of L. And we're requiring that the n sub G of X over here is at least as large as X. And that's what we're saying right here. So n sub G of X has to be at least as large as X for all the subsets X of the left side of our bipartite graph. And so we're going to prove this. And one direction of this is pretty much immediate. So this is an if and only if. So it does have two directions. We have to prove a forward direction and a backward direction. And the forward direction, we need to prove that if G has an L perfect matching, then for all subsets of the left side, subsets X of the left side, we have the cardinality of X is less than or equal to the cardinality of n sub g of X. So for the forward direction, if our graph has an L-perfect matching, then we can take some L-perfect matching, we can call it M, and we can take any subset X of the left side. We can take X right here, and X has some elements in it. And then we can look at what does M match them with. Because we know G has an L-perfect matching. So this matching has to match every element from the left side, including all the elements of X, because they're all elements of the left, because X is a subset of L. So the matching M, it has to match all of these elements of X. With something. And we can look at the set of those vertices that they got matched with. And these vertices right here, the number of those vertices is cardinality of X, because M is a matching. And those vertices, they're not just vertices, they are neighbors of the set X. So they are vertices that are adjacent to some element in X, because these are all vertices that are matched to the elements of X. And that tells us then, if we have cardinality of X vertices that are neighbors of the set X, then the size of this set, n sub g of X, has to be at least cardinality of X, because we have a subset of n sub g of X with cardinality of X vertices in it. Since all of these vertices here are neighbors of the set X, they're neighbors of some vertex that's in X. So our set n sub g of X has to be at least the size of the set of vertices here. And since we got the set of vertices from the matching M, the set of vertices has the same size as X. So cardinality of X. So the forward direction, an L-perfect matching giving us this inequality for all the subsets X of L, that's immediate. We're just getting that inequality, just using the matching on each of those subsets to give us a subset of n sub g of X that has size at least cardinality of X. So that's the forward direction. It's just a few lines like that. And the backward direction, we're going to prove that with induction. So to prove it by induction, we're going to have to do a base case and an inductive step. And the induction is going to be on the cardinality of the left side of our bipartite graph, so the cardinality of L. So the base case, we check it when the cardinality of L is 1. So we want to see, is there some matching of our bipartite graph when the part on the left has size 1? And we want to prove the if and only if in this case. And we already have the forward direction, so we only need the backward direction. And so we can assume backward direction for every subset of the left side. The size of that subset is less than or equal to the size of its neighborhood. In particular, we can take the whole subset. So we can take X equals L. And this criterion tells us then that the cardinality of L is less than or equal to the cardinality of the neighborhood of L. So that tells us that the vertex in L, in this case, when L just has size 1, it has a neighbor by the criterion. So there is a matching. We can just put that vertex in L with its neighbor. There's a matching of size 1. And that's a matching that's L perfect, because it has all the vertices in L and some edge in the matching. Because in that case, you only need one edge to pull that off. So that's the base case. Now let's look at the more interesting cases. So we're still doing the backward direction because the forward direction was the easy part. So here's our inductive step that we're about to prove. There's the setup. Our assumption for the backward direction is that the cardinality of x is at most the cardinality of the neighborhood of x and g for every subset of the left side. And we're just going to pick an arbitrary vertex on the left. So we have L over here, we have R over here, and then we just take some U and L. And by our assumption here, we can take the subset X to be the set just with the vertex U in it. And so we know by this criterion up here that the cardinality of that subset just with U in it, which equals 1. This is less than or equal to the neighborhood of that subset in G, which we usually write as neighborhood of U, like N of U. So the size of the neighborhood of U is at least 1 by that assumption. So we have some neighbor of U in our graph since it has size at least 1. So there's some V over here, and there's an edge UV. And V is also an R because it's a bipartite graph, so there's no edges from L to itself or from R to itself. So if we have that edge from the edge UV, and we were able to find a matching of size cardinality of L minus 1 in the induced subgraph with vertex set all of L minus U and all of R minus V. So in other words, if we were able to find some matching that matched all the other vertices in L to some vertex in R, then we would be done. Because if we have that edge UV, so I'll write this over here. So the edge UV plus a matching of size L minus 1 and the induced subgraph of G with vertices L minus U union R minus V. So that edge UV plus a matching of size cardinality of L minus 1 and that induced subgraph where the vertices are L minus U and R minus V. That would give us an L perfect matching in G. So we just take that edge UV and we take the matching of size cardinality of L minus 1. And that matching of size cardinality of L minus 1, it has to match all the other vertices of L besides U because it has size cardinality of L minus 1. And that would give us a whole matching that matches all of the vertices in L to some vertex in R. So that would be an L perfect matching if we could do that. So we can assume for the rest of the proof that we cannot do that. So we cannot find a matching of size cardinality of L minus 1 in that induced subgraph of G for which the vertex set is L minus U union R minus V. And using that assumption, we'll still show that we can find an L perfect matching in the end, but it's not going to be as easy as just combining the edge UV with the matching of size cardinality of L minus 1. So from here on, we'll assume that we cannot find that matching of size cardinality of L minus 1. And since we can't find that matching in this induced subgraph, so this induced subgraph, it's bipartite still, because the original graph is bipartite. And we cannot find an L minus U perfect matching in this subgraph. That's our assumption. We can't find a matching of size cardinality of L minus 1. So we can't find an L minus U perfect matching. So no L minus U perfect matching. That's our assumption in that subgraph. And by that assumption, that tells us, using our inductive hypothesis, that since there's no L minus U perfect matching in that subgraph, we must be able to find some subset of the left side of the left side of that subgraph. The left side of that subgraph is L minus U. So we must be able to find some subset X, a subset of L minus U, which has fewer than cardinality of X neighbors in R minus V. And if we know that in the graph G, the number of neighbors of X in G was at least cardinality of X. And we know that in this graph, this induced subgraph, where we restrict to L minus U union R minus V, the number of neighbors is fewer than cardinality of X in there. Notice that since X, this X right here, is a subset of L, it's a subset of L minus U, so it's a subset of L. But since it's a subset of L, all of the neighbors of X have to be in R. So we can say that X had at least cardinality of X neighbors in R, but it has fewer than cardinality of X neighbors in R minus the vertex V. And if the neighborhood of X had size more than cardinality of X, so if we had, let me actually put this over on the right side. So if we had and this should be, that should be cardinality. So if this was strictly greater than, if it was greater than cardinality of X, then if we restricted to that subgraph, so we can give that subgraph a name, it'll be convenient to name it, we'll call it H. So in that subgraph H, and this should also be a cardinality here, then we would be able to say if the size of the neighborhood of X in G was greater than cardinality of X, then since all of the neighbors of X are in R, then if we look in this induced subgraph, which takes one vertex only out of R, just the V vertex, so it just decreases the size of R by a single vertex, then the neighborhood of X in that new subgraph, so NH of X, that would have to be greater than cardinality of X minus 1, because we only took one vertex out. We only took the vertex V out of R. So it can only go down by 1, and being greater than cardinality of X minus 1, that implies that the cardinality of the neighborhood of X and H would be greater than or equal to cardinality of X. And we were assuming that that was false, so that's a contradiction, because we assume that this subset right here, X, had fewer than cardinality of X neighbors in R minus V. And that's same thing as fewer than cardinality of X neighbors in H, because that's what H is. H is this induced subgraph with vertex set L minus U union R minus V. And remember, this subset X, it can only have neighbors in R minus V. And when I say that, I mean neighbors in the induced subgraph H. So when we're talking about the neighbors of X in the induced subgraph H, they're only in R minus V. They're not in L minus U, because our graph's bipartite. So this is why the size of the neighborhood of x and g has to be exactly cardinality of x. So before we were able to say that it was greater than or equal to cardinality of x by the assumption at the top, but using this assumption about x, the fact that we cannot find the matching of size cardinality of L minus 1 in this induced subgraph, it gives us this x for which we can say the cardinality of the neighborhood of x and g is exactly cardinality of x. And then we'll give a name to the set of neighbors of x. We'll call that y. So x right here, here's x. And then the neighbors of x, all the neighbors of x, they'll go right here. They'll be y. And then we can look at the induced subgraph of G, where the vertex set is x union y. So just the induced subgraph that I just drew, maybe I'll put in a rectangle here. So this induced subgraph. We can use our inductive hypothesis on that induced subgraph. And we can note here that for all of the subsets of the left side, the x side, we have these inequalities are true. So the size of the subset is less than or equal to the size of its neighborhood, because we've included all the neighbors in our induced subgraph. So all the neighbors of our x are in y. So we still have this inequality true up here. And that tells us, since we have those inequalities true for all the subsets in that induced subgraph on the left, we must have an x perfect matching on that induced subgraph. So that induced subgraph where the left is x and the right is y, it has an x perfect matching. And we're going to use that to try to build our L perfect matching. So now we're going to look at subsets of L minus x. So we've dealt with the x part. We have an x perfect matching for the x part. Now we just want to deal with the L minus x part. So we can try to consider all the subsets of the L minus x part, and then somehow use the criterion up here with the inductive hypothesis. So we take some subset x prime in the L minus x part. And here's the claim. So this is the claim, and I claim this is not obvious immediately, but it's going to be clear because of the next part. So first, x union x prime has at least x cardinality of x plus cardinality of x prime neighbors in R. So why is this true? Well, it's true by our assumption up here again. So we know for any subset of L that the size of the subset is less than or equal to the size of its neighborhood. So we know the size of x union x prime is going to be less than or equal to the size of the neighborhood of x union x prime in G. And x prime is a subset of L minus x. So x and x prime are clearly disjoint. So cardinality of x union x prime is just cardinality of x plus cardinality of x prime. And we're just saying that that's less than or equal to the cardinality of the neighborhood of x union x prime in G. And that is how we can say that x union x prime has at least cardinality of x plus cardinality of x prime neighbors in R, because the size of the neighborhood of x union x prime in G is at least cardinality of x plus cardinality of x prime. And this neighborhood, all the elements of that neighborhood are in R. So all of them have to be in R, the neighborhood of x union x prime, because both x and x prime are from L. So that's how we can say that. And then we also had the fact that the neighborhood of x and G had the same cardinality as x right here. And we said y was the set of neighbors of x. So the neighborhood of x has the same cardinality as x, and y is the set of neighbors of x. So cardinality of y equals cardinality of x. So that's how I went from here to here. So we just said that x union x prime has at least cardinality, we'll say x prime plus cardinality y, neighbors in R. Then we can look at x union x prime has at least how many neighbors in R minus y. So if they have at least cardinality of x plus cardinality of y neighbors in R, and we take out cardinality of y vertices from R, then the number of neighbors is going to go down by at most cardinality of y. So the number of neighbors of x union x prime in R is going to be at least cardinality of x prime, cardinality of x prime neighbors in R minus y. So if we're taking cardinality of y vertices out of R, then the number of neighbors of x union x prime is going to go down by at most cardinality of y. So we have at least cardinality of x prime neighbors of x union x prime in R minus y. And then we can note that x has no neighbors in R minus y, because we defined y to be all the neighbors of x. So x has no neighbors in R minus y. All of its neighbors are in y, and R minus y is the complement of y and R. So this means that x prime actually, this x right here was just extraneous. It wasn't doing anything. So we can say x prime has at least cardinality of x prime neighbors in R minus y. And we just proved this for every subset x prime of L minus x. So we proved every subset x prime of L minus x, the size of its neighborhood in the graph when we restrict to, when we take the graph L minus x union R minus y. So the induced subgraph of G with that vertex set, we showed that every subset of the left side has a neighborhood at least as large as itself on the right side. So for that induced subgraph, we can apply our inductive hypothesis. And I'm going to clear a little bit there so we can see that. So we apply the inductive hypothesis to that subgraph on the vertex set L minus x union R minus y. And since all the subsets on the left have neighborhood in that subgraph at least as large as themselves, then we can find an L minus x perfect matching on this induced subgraph. So we take this L minus x perfect matching on this induced subgraph of G with vertex set L minus x union R minus y, and we take the x perfect matching on the induced subgraph of G with vertex set x union y, and if we call this one M, and we call this one N, M union N is what we want. So we just take the union of those two matchings. So we take the matching up here, which covers the elements of x, and we take the matching at the bottom, which covers the elements of L minus x. And together, they cover all of the elements of L. So every element of L is in some edge in the matching, which is the union of those two matchings. And that gives us an L perfect matching. So that brings us to the end of the proof. Thanks for watching.